Okay, so welcome to lecture number 14 of the course. And let's start with a very short summary of where we are, right? So again, the task is the same as before. So we have the PDE, which is given in this abstract form. And underlying the PDE, or along with the PDE, there is a solution operator, script G, calligraphic G, which maps functions to functions. So it takes in the inputs. Here it could be the coefficients A, the source terms F, and it churns out the solution here. So this is the setup that we are in. And since we are dealing with mappings between function spaces, as we have seen before, we have to be careful. In particular, what we have to do is to ensure this principle of continuous discrete equivalence that I've been droning on about for long. And we do that through this representation equivalent neural operator. So the idea is very simple, that instead of looking at mappings between function spaces, we do an exact correspondence or an exact equivalence by going through discrete spaces. For instance, functions on a grid. So you start with the continuous function space, you go down to the discrete space like this, you operate here, and then you go up back through some reconstruction operator, right? And this diagram should commute. So this is the basic principle. And we are still in the search of what can be an effective ReNO. So in the last lectures we saw that CNNs are not, because even the convolution operation is not preserving this structure, nor are FNOs. Even though the convolution operation preserves, the nonlinearities don't preserve this structure. So neither of them are ReNOs. We did see some examples, for instance, the spectral neural operator and DePonet, but they perform rather poorly. So the objective, as I said in the last lecture, is to find a structure preserving continuous discrete equivalent map, a ReNO, that actually works. And hopefully we will do that today. Of course, there are always issues with everything that one constructs. Okay, so this is the setup. We are trying to find something which takes as inputs functions, which churns as outputs functions, and it does it in the structure preserving manner, which is illustrated here through the diagram here. Okay, so let's do that. And to do so, what we are going to do is to essentially bring back convolutions. If you remember, both CNNs and FNO, they were doing convolutions, right? So the essential mode of operation was always convolution. So CNN did it in physical space and FNO in Fourier space, if you recall correctly. And then, sorry about this, I don't know why why it went back. Okay, so here we are. So there is convolution, and it's always followed by nonlinearity. So convolution, nonlinearity. And what we are going to do is to see if convolutions can really be, because both SNO as well as DePonet, they did not use this convolution, right? They sort of broke the structure of space, which is what I was trying to allude to in the last lecture. They broke the structure of space. Somehow we have to bring that back, the relationality between spatial elements. So can convolutions be brought back into the reckoning? And why is that? So before the rise of vision transformers and diffusion models, convolutions were essentially the main models in vision. So if you consider image processing, classification, generation, and so on, convolutions play even today a very, very big role in it, right? So this is one point about convolutions. Second, particularly when you do them in physical space, there is a concept of locality. In other words, if you think in terms of image or a one-dimensional function, then what convolutions do is that nearby points, they are taken together. So that neighborhood relations, locality, is somehow constrained. And of course, there is computational efficiency in convolutions, because essentially what you can think is, if you think of in terms of a matrix vector multiply, then convolutions, this matrix is going to be sparse, right? Extremely sparse, because it has this localization structure. So convolutions are computationally efficient. And also, one can realize that there are some links between convolutions, CNNs, and finite difference methods. Finite difference methods are a very popular way to solve PDEs. And it turns out that you can rewrite finite difference methods in terms of convolutional kernels. I won't do it here. This has been done some time back. So there is an intrinsic link between these methods. So given these considerations, it sort of makes sense that we bring back convolutions into the reckoning, right? We somehow bring them in. There is, of course, a big issue. If you remember, even in our last lectures, 2 lectures, we know that they are not ReNOs. CNNs are not ReNOs. There is some inconsistency in function space. And somehow we have to work with and we have to remove this inconsistency to be able to solve this problem in some sense. Okay? How do we do that? So this will be the main focus of my lecture today. Let me start by essentially saying convolution strike back. So I'm going to describe in the next half an hour, 40 minutes, this architecture which was proposed last year by essentially my lab. And this is called convolutional neural operators. And you'll see that it has many of these desirable properties that we aspired for. So in particular, it keeps convolutions. So it has all these nice properties, locality, computational efficiency, and so on and so forth. In addition, it's also a ReNO, or we are going to construct it in such a manner that it is going to be a ReNO. But remember that the reason why we failed last time is because convolution itself, so remember that we always have this, let's say, workflow, right? So we have convolution, we have nonlinearity. So what we have to do is to modulate these two. So remember that for CNNs, convolution itself was no longer structure preserving, and for FNO, even though convolution was structure preserving, the nonlinearity was not. So we have to work with both these layers or both these objects in order to ensure that the right kind of structure that we want is going to be preserved. And that is what is done in CNO, for instance. So the idea is, and I will describe it in quite some detail, but here is sort of a graphic. And again, the point is that we always have convolutions and nonlinearities. There are many other operations that I'm going to describe in some detail. So the picture, as you can see, is that there are many, many layers. As always, these are sort of layered. There is a compositional structure to them. And what we are going to do is to see how convolutions, so convolutions play a role here. This K is convolutions, and the nonlinearities are going to be given by this sigma. But there are some additional elements to it that I'm going to describe during the lecture. Okay, so let us start with where we stand. So remember that with ReNOs, the point is that you have to work with the right kind of function spaces. So the function spaces cannot be too big, otherwise we will not be able to retain the structure. So the function spaces, this is of course a special case, but it's a very illustrative special case. So what we're going to do is that we are going to build an operator. Let me call it as G or G star. I don't remember how did I call this. G star. This is operator that is going to take functions, 2 functions, and these functions are going to be band limited functions. So remember that I define band limited functions. So essentially what you do is you take a function, you take its Fourier transform, and you cut off the high frequencies beyond a certain point. So essentially for BW, this is all the functions. So U belongs to BW implies that the Fourier transform is the support of the Fourier transform. I should have used that. The support of the Fourier transform of U is contained inside minus WW, just for simplicity. It could be a vector space or a multidimensional space, of course. So we are taking band limited functions. This allows us to work with this continuous discrete equivalence, because for band limited functions, remember that we can essentially, the discrete version of it is essentially point values on a grid. Point values on a grid. So in other words, if you go back to the diagram, and this diagram is very important, that's why I keep on repeating. So if you have band limited functions here, so let me use another color, BW perhaps, then this is just functions on a grid. So little L2, functions on a grid. So there is a clear correspondence between the two, as long as these Nyquist conditions are satisfied. And Nyquist conditions say that the grid spacing is essentially less than 1 over 2 times the frequency, right? That's the basic idea behind these functions. So we are always going to operate between band limited functions, and my input here, U, okay, sorry for the notational confusion here, but okay, does not matter. So my input is given as a band limited function, and my output is also going to be a band limited function. And in between, I'm going to process it through different steps, through different layers, and through different objects, right? And so what are the building blocks? The obvious ones, which are similar to that of FNO, are these lifting and projection operators. So remember, the first thing that we do is that let's imagine that we are looking at the state of the weather. The state of the weather outside is given by several variables, essentially temperature, pressure, velocities, things like that. So there are a fixed number of, so this input here, so let's say that my u, which is the input, is some function. Let's say that this is a band limited function, which maps to the domain D, the domain that we are in, to some vector space. So this is to M, let's say. Okay, so this is the sort of, and D is some domain inside Rd. So this is, so there are m dimensional inputs, okay? Think of density, pressure, temperature, velocities, and so on. So the first thing that we always do is that these are sort of the physical features. There is no reason why this is the right kind of representation of the system in machine learning for a learning algorithm to work. So what one does is either to embed it. So typically what you do is that you embed it into a high dimensional feature space. Okay. So this is precisely this operator that it takes a u. So pu belongs to some r d in. Okay. So d in is some high dimensional feature space. D in is much greater than m. We already saw that in FNO. So you can think of it as adding channels or channel augmentation. So this is the first step, that you take your input, which has m features, and you embed it into a much bigger space, which is, let's say, D in. Let's say 4 features, you go to 20 features or 100 features or something like that. So that provides some effective coordinate system where the learning algorithm can function better. So this is, needless to say, almost in every algorithm, this is fairly standard. Okay? So this is the lifting operator. Then you work with this V0. This is the sort of the lifted version. So this has more channels than, much more channels than your original signal, right? Then you do your processing. These are the steps, the processing steps. And then you end up with some output after X number of layers, usually 8 to 10 layers, and then you have to come back to your density, your pressure, your velocity, the number of channels that you have, and this is typically you're back to your Rm, right? So this is the thing back, the projection back. So you take all these channels and you shrink them back. Now P and Q, this can be simple linear maps, that's the easiest way, tensors essentially, or you can take them to be MLPs, means in general MLPs. But at least in the implementations that we have, these are mostly linear maps. Okay, so P and Q, these are linear maps. They don't do anything fancy. They don't work with space at all. So they don't change space. So all that they do is they add channels or take out channels. So these are by definition ReNOs, means they don't affect the structure of space. So there is nothing fancy happening there. So is that clear? So this is a part of every package that you sort of associate a new coordinate system that is better able to learn features in the data. Okay, this is sort of standard. So now what we have to operate is, given these two operators, we have to work with the two essential ones. You know what, I have actually forgotten to start the recording. Okay, I have to somehow patch this. Okay, yeah. Sorry about that. People miss half an hour. Okay, coming back to, I will patch it up later. So essentially what you do is that you do this projections and this lifting and this projection back, right? So what is left then is that you have to work with convolutions and nonlinearities. Do you have a question? I can, no? Mm-hmm. Yes, I will just hold your patience a little, because I will talk about them, right? 10 is just a number that I threw out. It could be 3, it could be 6, it could be 12. I think the biggest models that we have probably have 16 layers. So it's sort of, it depends a little bit on the data that you have, it depends a little bit on the compute that you have, and so on. Okay, so now let us look at the key building blocks, because this lifting and projection, they generally come with the basic structure. So the key building block is, of course, the first key building block is convolution. So this is convolution in physical space. Okay, this is the difference from FNO, because we are going to do everything in physical space now, which is good because it keeps some locality. It doesn't matter what boundary conditions you take, and so on and so forth. And what is the contrast now? So remember, the contrast is always with the CNN, because the CNN, remember that this was the structure of the CNN. In the CNN, we had everything working at a discrete level, and as a consequence, we failed to have this structure preserving property. But let me now try to explain how the convolutions work. And this requires a little bit of time. So what we do is that we have continuous convolutions. So of course, everything is continuous. We have continuous convolutions, but of course on the space of band-limited functions. So in other words, you have to do a convolution. So you have f, which belongs to band-limited functions. You have a convolution kernel. So this is as before. So you have a convolution kernel kw. And then you have to do a convolution. So kw star f is nothing but the integral over d of kw x minus y f of y dy, which could be the same as kw y f of x minus y dy. So this is in the function space, right? But we have to do something at the discrete level. So what we do, and this is the key trick here, there are two key tricks. The first is that our convolution kernel itself is actually discrete. Okay? What does that mean? That means that this kw function, kw of z, for instance, is nothing but a sum of some kj delta. I'm just talking in 1D, but this is in 2D, 3D, 4D, whatever the generalization is obvious. Zj. Okay? So what you do is that you still keep the kernel discrete. In other words, so this is the Dirac. Okay? All of you should know this notation. This is the Dirac delta function. So in other words, if you have a picture, you pick some points. These are generally points on a grid, because remember that we have band-limited functions, so we have points on a uniform grid. And then essentially what you do is that you have different values at these points, some k2, some k1, k4, k3, k4, something like this. You fix the size of the kernel. The size of the kernel is fixed a priori, and these are discrete points. So what does that mean? So if you now evaluate this integral here, follow. So this is discrete. So this will simply mean that this is a summation over j, kj of f of x minus zj, right? So this is what it is. So what you're doing now is that you're fixing the discrete kernel as before, as in a convolutional neural network, but you are acting it in a continuous manner. Okay, so this is sort of the first key point that we are with band-limited functions. So we are always having a clear correspondence, a clear sort of mirroring between the continuous and the discrete. But why is this a ReNO? Means how do we apply it on different grids and so on? So first of all, I will explain it in two stages. So in terms of the commutative diagram, this is fairly straightforward, because you take band-limited functions and it is straightforward to compute, it's straightforward to calculate, that once you take this discrete kernel, then this mapping that I defined here is going to map to band-limited functions. It's a one-line argument. You can check it in the paper, for instance. But at the discrete level, what happens is that band-limited functions are related here by the sinc filters. So remember that this size here are given by sinc functions. Or you can think of a band-limited function f of x as the summation of f of xj, sinc of x minus xj, roughly speaking, right? So this is the basis interpretation that we have, and because there is this clear correspondence between point values, it is a little argument to show that even this entire diagram, so you can come here, you can work here, you can go like this, or the other way around, it does not really matter. It is the same problem that is being done. But okay, so this structure, this algebraic structure is very, very clear, but how does it contrast with CNNs? Means what is the difference that we did with CNN that changes things, okay? And this is best explained. So remember that we have this discrete kernel, okay? And we are going to keep this kernel fixed. We're not going to resize the kernel, as some of you suggested. what we are going to do is to resize the functions. Okay, so the inputs. So here, remember that this was the issue with the CNNs. Let me revisit this. So what we did was that I took my kernel, similar to what we have before. I took my kernel, I took my signal, so I took the, let's say on a coarse grid, I took these values, multiplied them, and I got some answer. And then I took different values, because now you are on a finer grid. I multiplied them, and of course I got a different answer, because I was not changing the kernel, nor was I changing the input signal. So now the difference here is because we are working with these band-limited functions, and because there is a clear correspondence between the continuous and the discrete, this is how you do the convolution operation. So let us say, so this is as before. So okay, so this value is as before. Now when we work with this, let's say new signal, what you do is, because you have a correspondence between the continuous and the discrete, which is exact if the Nyquist barrier is satisfied. So what you will do is that you will take this function, you will take these point values. Remember that you take these point values, you're going to lift them up here to the continuous level. You are going to pull it down to the discrete, right? Because then by the sinc filter you can pull it down to the discrete, and then you apply the discrete kernel again. Okay? And because these two functions are identical, what happens is that by reinterpolating like this, you are going to essentially do this operation here. That first, you start with your discrete inputs, pull them to the continuous function space, then resample them to the new or the coarse grid, which was your original grid, where the kernel is defined, apply the kernel, push it up again to the continuous case, and then go back. Okay? So this is the reason why by working with these discrete kernels, and while at the same time keeping the convolution kernel fixed, but resizing your input functions back into the size of the convolution kernel, you are able to enforce that this ReNO property is satisfied. Okay? So it's somehow the fix was in the understanding of the problem itself, because we understood that the problem was that you are working with different function spaces, different grids, and you are using the same kernel. Now all that you do is to resize back to the same grid. You can do that because you have this band-limited functions. And then when you do that, you can see that you can apply the same grid just by reinterpolating. You get back the original function. So is that point clear? So in other words, this evaluation is not done directly. It is done like this. So of course, obviously, this ReNO property is going to be satisfied. So convolutions are done in this particular manner. And these are sort of the key points. Oh, sorry. I'm very allergic, so it's not a cold. Okay, so this is the key point behind the convolutional layers, that you have this sort of resizing of the input rather than resizing of the convolution kernel. Okay? The kernel is always going to be fixed. Or this is one way, of course, the way in which we implement. Perhaps there are other ways where this can be done. Okay, that's so much about the contrast with the CNNs, how we change, and how this is kept structure preserving. Now, what about nonlinearities? Because remember, there's always convolutions and nonlinearities. So now we fixed convolutions, but you can say, okay, what's the big deal? Because in FNO, convolution was already fixed, right? So there's nothing new that is happening. So, but the new is also at the level of the nonlinearity. And this is where interesting things happen. So let me give you a quick recall. So if you remember for FNO, so this is a quick recall. Now I really need to, you guys need to really focus. So if you recall, sigma, this is your application of the nonlinearity, was a mapping, you take an f, right? So you take a function, you apply the nonlinearity on the function, you evaluate it at a point x. This was nothing but sigma, your usual nonlinearity, applied on f of x. So this is how you did it in FNO. So you took a function, and you just applied pointwise ReLU, for instance, or some other activation function. And remember that this was the problem then. The problem was here. So the orange here is the signal, the function that is there. And then you apply nonlinearity. Let's focus on ReLU. Smoother nonlinearities don't make a big difference, but you take ReLU, and then you get the function in blue. So all the negative parts are copped out, right? So this is the action of ReLU. But when you look at it in Fourier space, remember that we are between band-limited spaces. So if you go between, so what happens now is that the original function, the function in orange, it was between minus 20 and 20 in frequency. Okay, it was capped because we just took band-limited functions. As soon as you took ReLU, what happens is that ReLU is a nonlinearity. Just imagine if you have the square, anything between minus 20 and 20, sine 20x squared becomes roughly sine 40x, right? So you introduce higher frequencies. Of course, what happens is that the coefficients of these higher frequencies could be small because the function has some decay properties, but you still see that there is some leakage outside. So for instance, if you take 40, for instance, here, you can see that there are non-zero frequencies. Even at 60, there are non-zero frequencies. So what happens is that nonlinearity breaks the band limits. So all this nice picture that this leads to aliasing because this continuous discrete equivalence is going to be broken in this particular case. Instead, so what are we going to do? How do we solve this problem now? So the solution of the problem is in identifying the problem itself, just like we did with convolutions. So here is the idea. It's a very simple idea. What if, at the application of the nonlinearity, instead of working with a pointwise nonlinearity, we do the following? Okay, so remember, so this was my Nyquist barrier. This is the Nyquist frequency, outside which, as you can see, that there is leakage, right? So what if, during the application of the nonlinearity, I allow my frequencies to grow in some manner? I allow my functions to have higher frequencies. In particular, let's use double the cutoff. Let's go to 40, right? If you go to 40, you can see that the frequencies beyond 40, it's still not capped because ReLU, you know, it's infinite, the response is going to be infinite. But if it would have been a square, this would have been between minus 40 and 40. But now, the higher frequencies, the leakage here is much smaller compared to the original leakage that was here, right? So you would expect that the effect of aliasing would be reduced. Okay? So the idea is to somehow accommodate this feature of nonlinearity. What do nonlinearities do? They take a signal with k frequencies and they increase the frequencies. So then when we apply it, we know that the frequencies are going to increase. Then of course the nice structures that we have are lost. There are aliasing errors. So what if we do the following? That we start with a function, allow it to have higher frequencies, artificially, potentially, apply the nonlinearity with these high frequencies, and then bring back to your original frequencies by using a low-pass filter typically, right? So this kind of an arrangement will imply that we will leverage the fact that new frequencies are created by sort of stemming it in the beginning. We say, okay, fine, new frequencies are created, so what? Because I allow for that, okay? So this is roughly the intuition behind it. And the idea, and to carry this out, these kind of ideas were around in the world of vision, but we brought them with this sort of context at least. We provided this kind of context and this clear mathematical understanding of these ideas. So what we are going to do is that we are going to apply two key operators, which are going to be new sort of objects that you have probably not seen before in this context. And this will be what are called upsampling and downsampling operators. So upsampling is allowing for the creation of these new frequencies. Then you apply the nonlinearity, and downsampling is coming back to your original frequencies. Because remember, at the end of the day, I am always working between these band-limited functions. So I have to somehow come back to my original band. But while doing so, I am introducing these new frequencies, and these new frequencies are through this upsampling and downsampling operators. So before I write down the expressions, let me try to explain what it is. Perhaps I can use a figure, maybe this one. Okay, so this is the nonlinearity. This is the nonlinear activation module. Activation module of CNO. Okay, so what does it do? And please try to focus. So you're given your input, you do the convolutions. Convolutions keep the band. This is what I have kept on saying. So you do a convolution, and then you apply this activation module, which is capital sigma. right? So what you do is your signal, your input to this layer, to this band, to this module is here. So this is a function with, just for illustration here, we have taken 10 frequencies or 8 or something like that. So these are given by these points, or 4 frequencies, and they're evaluated at 8 points. So what upsampling is going to do is to increase the number of frequencies. If you increase the number of frequencies, you can evaluate at more points while still keeping the same structure, right? So trivially, if you have access to a continuous function, it simply means evaluating this continuous function at more points, right? So these are the new points as you can introduce. You're introducing a new grid here, okay, depending on which band you want to go to. So this is done by saying that you want to double the band, but that need not be the case. You can increase it by a factor of 4, by a factor of 8, depending on the nonlinearity that you have, depending on the problem that you have. So you have this additional introduction of frequencies. In the continuous case, you do nothing because your function is anyway defined at all these points. But in the discrete case, you have to do some sort of an interpolation, okay? And then you apply the nonlinearity. This will be pointwise. Okay, so the upsampling is a non-local operation because you are introducing new frequencies, and this is not done in physical space, it is done in Fourier space. So this is new frequencies, non-local. This is still local. You can apply ReLU, GeLU, whatever nonlinearity swish, whatever nonlinearity that you have here, right? Nothing strange here. But now you have allowed for these high frequencies, right? So this means that even if high frequencies are created, they remain within the same band, ideally. Then you have to come back to your original function, and this is again the sinc interpolation, because now you have these functions which are defined on this new grid, roughly speaking, and then you come back to the original grid. So you take the functions, you take the sinc interpolant and project it back. So this is your downsampling, okay? And this is a way in which you can go from a band-limited space to the same band-limited space while artificially growing frequencies and then quenching them later, okay? So this is roughly the intuition that goes in. Of course, you can, to realize it, you need some formulas, and these are probably given here. So as I said, at the continuous level, upsampling is nothing because you are just evaluating a function at new points. So this is your original band, but this is your new band, okay? This could be double. In practice, actually, we say it to be double, but you'll see that there is a subtle point about whether it should be double or 4 times or 8 times and so on and so forth. So this is straightforward. In discrete terms, you have to do this with some interpolation. And this is interpolation with sinc. I think you saw that in the tutorial on CNO. And downsampling is again an interpolation procedure because you have to go to the sinc functions and then you project them back to the original points. And this is again done through this, again done through this formula here. Okay? But the detail is not important. What is important is the intuition here. So at all times, we have this upsampling and this downsampling operations. And these two things are very, very important because they have to work in tandem. Now, it turns out that, for instance, if my nonlinearity was a square, okay? If my nonlinearity was a square, I know exactly that as long as this omega bar is greater than or equal to 2 or omega or w bar is greater than or equal to 2w, then this entire process is completely a ReNO. Why? This is for a square nonlinearity. I'm going to illustrate it for other nonlinearities in a bit. Because what do you do here? You go from w to 2w. This is, and this is done by this upsampling, and this is precisely this sort of lifting operation in some sense, or raising it to a higher frequency, which is trivial in some sense, because of course these functions function with 20 frequencies is contained inside functions with 40 frequencies. There is nothing to be done here. Then you apply the nonlinearity. So now remember that since it is 20 frequencies, when you go to take a square, it will have 40 frequencies. So this is of course well contained here. This mapping is between w prime, bw prime to bw prime, and then from 40 frequencies you can always come back to 20 frequencies by using this interpolation. And this is precisely the discrete version of these nice operators, which is what I just described. So of course this entire thing commutes, and this is why this particular realization is a ReNO. Now just imagine that instead of applying the quadratic, the nonlinearity was not quadratic but the power 4th. then of course this W prime would be 4 times W, right? Similarly, if it was power 6, it will be 6 times W. So if you take any polynomial essentially, then you can compute based on the highest degree of the polynomial what this W prime could be. So for polynomials, this is exact. This construction is going to be exact. Of course, it is going to be expensive because you have to have 4 times more grid points, 6 times more grid points, 8 times more grid points, and so on. So you pay a cost. It's not for free. However, if you take rational functions, so polynomials, this is exact, right? If you take rational functions, if your sigma of x is some polynomial divided by another polynomial, you can still do this because you have polynomials, so you can solve a nonlinear equation by Newton. You have polynomials on the left, polynomials on the right, and you can still do it exactly for rational functions. But if you take things like ReLU and Swish, for instance, can be approximated by a biquadratic polynomial, then, of course, what happens in that particular case is that if this W bar goes to infinity, of course, everything can be approximated by polynomials, and you can do this. But in practice, you cannot go to infinity, right? You have to fix a band. So you will have some error, but as you can imagine, this error will be smaller than it would have been if you did not do this upsampling. Because if you did not do this upsampling, then these high frequencies would have corrupted your signal, right? But by doing this upsampling, even with double, then you sort of quench these high frequencies and you're left with low frequencies. So this is not exact, it's an approximation, but in practice we saw that nothing changes if you just take 2, you see. So the frequencies are high enough, or the coefficients of the frequencies are low enough. As a consequence, you don't really need to process beyond twice the number of frequencies. But in principle, you can do it for any order, okay? If you have polynomial or rational nonlinearities. But if you don't, you have to make some approximations. But you have to reduce the aliasing error. And you'll see that in the numerical experiments in the next part of the talk, this is going to be clear. So this is how you are going to sort of do the convolutions, and you're going to do the nonlinearities. And you have to put them together, okay? So as you can see in this very simple structure, I start with a signal. I raise it by augmenting the number of channels, do a convolution, then apply the nonlinearity, and then again you can see convolution, nonlinearity, convolution, nonlinearity, till I end up with some stop, and then you go back to your original functions, okay? But so this is the plain vanilla architecture that you can use. But as you'll see, I'll take a break now, and let's meet at 10 past. You'll see after the break that in order to have a practical architecture that works, these basic building blocks are not enough. These basic building blocks of convolution and nonlinearities with this upsampling and downsampling are not enough. We have to put them together in a more intricate manner in order to sort of have some proper processing of the signal. But this is after the break, and let's meet at 10 past, okay? So, and see how this is done in practice. This is in principle. I've given you all the bases in principle, and now we have to take it and look for a practical architecture. But that's after the break. Okay, so let's restart. So as I said before the break, what we need to do is to put together these ingredients that we have, convolution and nonlinearity. And we do that in a very sophisticated manner because we know from computer vision, because these ideas of using convolutions and nonlinearities come from computer vision, that this has to be done in a much more intricate manner. You can't just stick a convolution next to a nonlinearity, put them in layers, and get the results that you want. Okay, so here is how it is in practice. That's why it's more complicated, right? So as you can see that this has this sort of a UNet type architecture. This is what works from long experience in computer vision. So the idea is that you have to do multi-scale processing of your signal. So in other words, if you have an image or any signal for that matter, it has structures at many scales, right? Even if it's a band-limited function, a band-limited function might have structures, non-zero structures at 30 frequencies or 40 frequencies or 50 frequencies, depending on the problem that you have. So in that case, what you have to do is, from computer vision, people have realized that you should process these frequencies somehow separately. So in some cases you process the high frequencies, some cases you process the low frequencies, and you put all of them together. And this is done in this sort of a U-Net kind of an architecture, and let me try to explain. So the building blocks are exactly the same. Upsampling, downsampling, nonlinearities, convolutions, it's exactly the same kind of a structure as before, right? So what you do is the following. Let me first give you the heuristics, and then we can look at the details in a second. So you have a signal, which is, of course, in multiple scales, usually. And then what you do is some sort of a scale separation, and then processing at different scales, and then mix them up. Okay? So, of course, this is your signal. It is 4 channels, for instance. The first thing that you do is through the lifting, you add more channels. Okay? So that is, you provide better coordinates for the learning system so that it can learn better. So this goes without saying. Then there are different kinds of layers here. So as you can see that they have some names. Let me even expand it further so that you understand it. So the first layer here is what is called an invariant block. Okay. So this is, as you can see, this is a dark red color. I can't see it at this resolution, but I think you guys see what it is, right? And what does it do? It takes a signal, band-limited function. It puts a convolution, and it puts a nonlinearity. And the nonlinearity itself, the activation, has this upsampling and downsampling layers, right? So this is what we have constructed. And when you stick these to convolution and nonlinearities, convolution is a ReNO, nonlinearity is a ReNO. When you add them together, of course, when you compose them, you still get a ReNO. So this is the first thing that you do. So you take the input, and then you just apply this convolution and nonlinearity. This is what you would expect, and you would think that I just stack these together, and then I get my architecture. No, we have to do a little bit clever stacking, and this is done in this layer. It is called roughly an encoder. Okay, so this part is what is called an encoder, and this part here is what is called a decoder. So what the encoder does is that there are 2 things it does. First, it takes the signal, and it keeps on, let's say, downsampling it. So it keeps on applying low-pass filters, but at the same time, so it also adds more and more channels. So essentially, this visually, just to represent the cartoon, the height of these boxes is your resolution. Okay, so the height of these boxes is your resolution, and the width of these boxes is the number of channels. So in the beginning, you have been given some resolution, I don't know, 128 squared, and then you just add more channels, right? And then here you keep the same resolution, keep the same number of channels, do some processing. But now you do some processing by reducing the resolution. Let's say you go from 128 squared to 64 squared. That's why you do this with this downsampling operation, right? So this is what is called a D block, this one here. This is a downsampling operation, but you increase the number of channels, okay? So you add more features, but you just process some scales in the signal, right? And this is what is done here. So this is this downsampling block. So you take the function, you do a convolution, you do a nonlinearity, and you do a downsampling. So you reduce the resolution. This is okay, means you're just reducing the resolution. You are keeping the same band limits, so it is still a ReNO. But what you do is that you increase the number of channels, okay? And you keep on doing it. So you take 128 squared, in the next one you go to 64 squared, then you go to 32 squared, 16 squared, 8 squared, and so on. Somewhere you have to stop, of course. And this is what is called the bottleneck. This is called the bottleneck. So the idea is that you, at different resolutions, you're processing different features, which is very clear from vision, right? Because what do we do in vision? There are, if you look at my face, there are some gross features, for instance, the outline of the face, the outline of the hair, and so on. And there are some sharp features, then the exact location of the nose, the exact location of the eyes, and so on. All that it says is that different parts of your network are processing different inputs, okay? Some are focusing on the broad features, some are focusing on the sharp features, and we think of functions, mathematical functions, in the same manner. High frequencies, low frequencies, different places I am processing different things. Okay, so this is this down D block, okay? It consists of convolution, nonlinearity, and downsampling. But downsampling, you have already seen before what it is, right? This is this interpolation with the low-pass filter. And you go in this manner, as you can see, I took a high-frequency signal, and here I'm just processing some parts of the frequency. Here I'm processing even lower parts of the frequency. So this is the decoder part of it, which is very standard in this UNet architectures. But now you process, and you have to build it up again, right? So you have to get back to your 128 squared. Encoder, sorry, I should have said. So this is done by the decoder. So you have to now take the low frequencies, combine them with the next high frequencies, combine them with the next high frequencies, combine them with the next high frequencies, and so on. And this is done by using what are called upsampling blocks, U blocks, as you can see here. So this is this part here. Again, convolution, nonlinearity, and upsampling. What do you do in upsampling? You increase the resolution. So you go from 32 squared to 32 squared in a gradual manner, and you reduce the number of channels. So as you can see, you are making something which is fat and short into something which is thin and tall. Okay, that's roughly the sort of heuristics here. So this is sort of a very basic UNet kind of an architecture where we take, and all of this, each of the ingredients are ReNOs, right? Because we are taking nonlinearities, which are ReNO, downsampling, upsampling, and the convolutions, right? So this is the basic structure. But this is not enough, because there are some new features that you are also adding. And what you do is you use what are called residual connections, because what you're doing is that you're stacking a lot of layers. So when you compute gradients, you have to do backpropagation, right? So you have to do backpropagation. When you compute gradients, you have a lot of layers. What happens is that the gradients could explode or vanish. You have seen this in some of the first lectures. So when you have so many layers, you have to put in residual connections. And these are done through these R blocks. These are here at the bottleneck. These are also here at all the intermediate frequencies, okay? So what is happening at this bottleneck, for instance? So you take the signal, you apply a convolution and a nonlinearity as before, but you keep the signal, okay? So that means that the gradient properties, there is another channel, another route through which the gradient can come, so you don't have the smallness of the gradients. So this is roughly the heuristic here, and it is done at all levels, okay, not just at the bottleneck, because in a traditional UNet, these parts are not there, okay? These are our sort of fixes here, because we want to keep a lot of high frequency content in the signal, otherwise the high frequency content gets lost. So you have these residual connections, and then you have them at every sort of intermediate layer, okay? At every intermediate layer, you have these kind of residual connections. Of course, all of them are ReNOs, but these are in order to ensure that this multi-scale signal processing really kicks in. That's why it's a very elaborate architecture. Without that, you won't get the sort of results that you will see in a moment. In addition, you also have, as in UNets, what are called concatenations. So what are these? These concatenations is, so for instance, let's focus here. So now you have applied this ResNet. So this is short and fat, and then you want to make it tall and thin, but you have also kept some features from this side here. So from this frequency here, and you just couple them together, okay? You couple them together, you concatenate them, and you transform them back. Same here. So you have something which is short and fat, you make it to be tall and thin, and then you have some features from here that you're processing through ResNets, and you just concatenate them, and then you plug them up, and you keep on doing this, right? So this is a very, very elaborate architecture in some sense, because it takes into account the fact that you have information which is contained in different frequencies, okay? Yes? Yeah? Is what? Suppressed in the notation. There is no, how do we do it? Yes, it's just by, how do you do, you did it also here, right? Yes, but so, it's the same one every time. No, you have, these are learnable mappings. So what you take is a linear layer, which sort of increases the number of channels, it reduces, I think in the tutorial they covered this, if I'm not mistaken, they must have covered it. So when you look at the code, all that you do is that you have learnable transformations, which takes a 10 vector, and makes it into a 20 vector. You see, these are learnable linear transformations. They don't do anything with space. So these ReNO properties are only dependent on the spatial information, right? These are just adding channels. So you can always do that by using learner. These are all learnable. So these architectures have lots of parameters. Means you will see in some of the examples that these have lots of parameters. I think the biggest models that we are running have like 400 million parameters. So this, as you can imagine, these are not cheap in that sense, right? They're not cheap to train. They're not expensive to infer. So I would say that these are details, okay? These are details in order to get sort of good performance. Even if you don't have all of these ingredients, if you just stack things together, you'd still get something which is reasonable, okay? It's just that these things increase the ability of this network, of this operator, of this model to do this kind of multi-scale information. Oh, damn it. To do what is called multi-scale information processing. Because that's the name of the game, that you have multi-scale information processing, you have information at different scales, and you need to process them in a neat manner. So otherwise, all these layers, all these blocks, and so on, these are in some sense details. You know, when you work in machine learning, it's very, very important to have architectures that have the best performance, that are state of the art, and then you need these kind of additional features. But even the bare bones version of it, which will just be convolution nonlinearities, that sort of works. Means it's not, it does its job in some sense. But now you have to remember that it was the same with FNO. In FNO also there were these additional elements that were there. You had some residual connections somewhere, you had some MLPs somewhere. These are all there to add information processing capacities. Okay? Yes, James.
Is it possible to make FNO into ReNO using like the upsampling, downsampling trade?
Yes, you can. You can. You can easily do that. We have done that, and yes, so that functions. You can do that. It made it into a ReNO, but it worsened the performance. Because what it did is that it clipped off some features, you know. So the idea is that by making things into a ReNO, you have to sort of take out some frequencies, right? Means you have to take out information. Otherwise, some of the information is lost. So all these other ingredients, they bring back this information. Okay? Somehow you have to keep the high frequency content. And by the way, I forgot before the break, I forgot because, there are many things to say. But the whole point about, maybe I said it and didn't emphasize it, the whole point of this activation layer is that now it's non-local, right? Earlier it was local, means because you were just applying a function pointwise. Now, why is it non-local? Because when you take a function at a fixed number of points, you increase the number of points essentially by this upsampling procedure, then it's local. But then again, it's non-local because you're going back to the function and coming back to the... So this is a non-local, is a genuine operator. It's not just what is called a Nemetsky operator, which is the application of a function operator on a local function. So this is somehow the key trick in order to make this work. So again, I emphasize that these are details. This does not... It affects a lot of the performance, the actual deployment of these architectures. But in principle, it does not change the flavor. Okay, the flavor is still contained in these basic building blocks that I explained before the break. Good. So I proceed. Yes, absolutely.
Is there a way to say how much you have to downsample so like for the
Yeah, you can. There are different choices here, right? But at the end of the day, you have only a finite amount of compute and a finite amount of mental bandwidth to work with these things. So what you do is it's essentially a binary processing. So your images are always at resolutions which are powers of 2. So it makes a lot of sense to use powers of 2 in this, right? So let's say that you have an image which is 1024 squared by 1024 squared. It's a lot, right? But what you do is that in the first step, you reduce it to 512 squared by 512 squared, then 256 by 256, and so on. You could do it for any. There is no, in principle, this upsampling, downsampling need not be done for just in the powers of 2. But you can imagine that in order to have an optimal implementation, caching, and so on, it makes sense to have things in powers of 2. But otherwise, you can always go from 100 to 80. You can always do that. but it's not optimal, in terms of how you retrieve information from the cache, how you store things, and so on. There is also a implementational perspective to it. And people who do computer vision, for instance, they have to work with images. For instance, Sora is working with 1920 by 1920, 2000 by 2000 images. They are doing this kind of processing because they need to. You cannot push in 2000 by 2000 images straight into a transformer. So they do this kind of dimensionality reduction, information compression in an efficient manner, because otherwise how will you, so usually powers of 2 are the trick, okay? So you use the powers of 2, but there is no, in principle you can do anything. Further questions? No? Okay, let's have a quick look at what are the properties of this construction. So again, as long as you have polynomial or rational nonlinearities, by construction, as I explained before the break, by construction, you get a ReNO. Of course, if you don't have polynomial nonlinearities or rational nonlinearities, by construction, you only get something approximation, right? But this is obvious. What is also important here is that there is a universal approximation theorem. I did not focus so much on the theory. Last year I did, but this year there is little time. So what is the meaning of this universal approximation theorem? So we have explained that in the context of functions, right? So essentially for functions, as long as the function is continuous, there was a neural network which would approximate it to the desired accuracy. You can do the same for operators. Okay, so now you can think, okay, you have continuous operators. So this is, of course, how do you define continuity? It's in the right kind of function spaces. So here we are using Sobolev spaces. This is a detail, it's not important. But essentially, let's say that your operator is from x to y. And then a continuous operator would be if you take, essentially, roughly speaking, if you take g of v minus g of v prime in y will be small if v minus v prime in x is small, right? So this is roughly the mental image. So if the inputs are close to each other as functions, the outputs are also close to each other as appropriate functions. So that would be the definition of continuity. So we go a little bit further, means you can do that, but ideally you want what is called a modulus of continuity. That's why there's this continuous plus, which means, roughly speaking, that this is not exact, but it is gv minus gv bar in y behaves like little o of v minus v bar in x. Okay, so you essentially, if this guy goes to 0, there is a modulus of continuity, there is a rate at which this guy goes to 0. That's all. If you have this property, then you can prove that CNO, FNO, DPONet, all of them are somehow universal approximations. They satisfy this property. This is an analog of what happens to finite dimensional vectors, right? So a neural network was approximating functions, which are mappings between finite dimensional spaces to arbitrary accuracy. What we are showing here is that a neural operator, CNO, FNO, and so on, they can do the same for operators. Okay, so it is one level higher, but the principle is the same. And anyway, the idea of the proof, I don't have time for this, but it's essentially by saying that your operator is going to be very well represented by mappings between band-limited functions. Okay, so because there is this mappings between band-limited functions, which bands depend on the underlying function spaces, and then you use the universal approximation theorem for neural networks and project it back. So essentially, that's the basic idea. And for CNO, there is code. You have already seen the code, and you are going to experiment with that also for your forthcoming exercises, right? So this is the thing with the theory as well as with practice. Let us see whether these things work in practice or not. And I'll show you some numerical experiments for the rest of the lecture. Okay, the first thing is we go back to this very, very simple problem that we had before, random assignment. This was just to show that FNO, for instance, and CNN, these were not ReNOs, right? So you train at a certain resolution, which was 61 squared, and because the image was at 61 squared, and then, okay, And then you could see that as soon as, of course, here the Nyquist barrier is broken, so nothing is going to be a ReNO because there is no one-to-one correspondence between the discrete and the continuous. But here, when the Nyquist conditions are satisfied, you are taking a finer grid than what the signal requires. Then what happens is that both CNN and FNO, these were not ReNOs, right? As soon as you change the grid, even by one grid point, the errors were amplified. But SNO as well as CNO, these are, by definition, they are constructed to be ReNOs, and you can see that they were able to keep it at machine precision. This aliasing error was 0 to machine precision. So this was completely expected because we have constructed things in such a manner that this property is going to be satisfied. Okay, but let's look at some real numerical results. Let's start with the Navier-Stokes equations. So all of you should know what these equations are, but if you don't, let me write it down. So because they come in again and again. So this is ut plus u dot grad u plus gradient of p equal to 0. The divergence of u is equal to 0. And u is the velocity, so this is ux, uy. These are the two components of the velocity. And p is the pressure, so this is the velocity. This is the pressure, so a lot of fluid dynamics is modeled by the Navier-Stokes equations. And then we have the vorticity, because we are going to visualize things in the vorticity quite a lot. So this is the curl of the velocity, curl of u. Okay, so in 2D, this is a scalar. In 3D, this is a vector. But perhaps I will have time to show you some 3D results at the end of the course, but let's focus on the 2D. So this is the operator. So it takes in, I'm just showing one component because otherwise visualization becomes difficult. So this is some ux at time 0, and then I am showing ux at time 1. Okay, so this is my operator. So it takes the two velocities and it churns out the two velocities at a later time, at a fixed later time, 1. And this is the vorticity. So this is the vorticity at 0 and the vorticity at 1. So this tells you what's happening. So you have some shear layer, and because of the shear, the vortices are generated. So these are the vortices that are generated. So this is a nice problem. It's sort of non-trivial, but at the same time, it's not ultra difficult, right? So now we apply different architectures on it. So we have CNO, FNO. You saw both of them. By the way, this is not the correct answer here. For some reason, I have got the wrong errors, but you'll see the correct errors at the end. I made a mistake. And then we have UNet. So what is UNet? UNet is just the same architecture, but without the upsampling and the downsampling. Okay, so this is no longer a ReNO. It's exactly the same, but you kick out the upsampling and the downsampling, use a straightforward convolution, and you use a straightforward nonlinearity. So this is an ablation on CNO. It does not have this ReNO property, but it has every other feature. Okay, and then there is also a fully connected feed MLP. So this is roughly a MLP, roughly. Of course, very expensive as a consequence. And then we have DeepONet. And you can see that just qualitatively, that first of all, DeepONet, we have seen this before, it completely fails. So the CNN is nothing but the UNet, okay? So this completely fails, just approximates the mean, and that's the result why you get this kind of large errors. It's not, also in the last lecture, I tried to explain why that could easily be the case, because you lose out all the spatial relationships somewhat. Now, FNO does a good job. It has 4% error, which is reasonable here. What it does, unfortunately, is that there are some artifacts, some aliasing artifacts. For instance, this feature here, there is some artificial features here, some ringing here. This, we believe, is a sign of aliasing. UNet also has the same kind of features. It has this aliasing again. You can see here, and so on. A CNO doesn't have these things, right? It provides a good approximation. Of course, an approximation. It's not exact. And this is done with 1,000 samples. Okay, you need some training samples. So this is done with 1,000 samples. And you can see that this is a good approximation. I think these numbers are not exactly correct. You'll see the correct numbers. I was probably making a mistake with respect to the... But so this is what you see at a fixed resolution. And this is 128 or 64 squared. I don't remember. Now remember that what we really need to do is to 64, okay, because I see that that's the resolution. What happens when you change resolution, right? So when you change resolution, as expected with the UNet, the errors really went up, right? Because it's no longer a ReNO, you have this aliasing effect. So it is not a neural operator because we did not have these ingredients in place. FNO, somehow because it's partially a neural operator in some sense, because at least the convolution does not add high frequencies, only the nonlinearity does. And here the frequencies are not so bad. So here this part, you have small errors, but they are non-zero errors. This part, you have lots of errors, you know. So it really is not able to understand when you are at a lower grid resolution what is to be done, even though the Nyquist conditions are satisfied. Nyquist conditions are satisfied all the way up to 32. So that's not an issue here. Okay, CNO as expected, even though we are using nonlinearity, I don't remember now, I think it was Swish, which is not exact. It retains the errors of no aliasing errors up to more or less machine precision here. Okay, so this is as expected, it does its job. And you can see that with the spectrograms. What are the spectrograms? I just take the output and I plot the frequencies, okay? And this is in logarithmic scale. As you can see, it goes all the way from 10 to the power minus 3 to 10 to the power minus 7. And you can see that between minus 32 and 32, a lot of frequencies are represented. Most of the frequencies are in this central region, as you would expect, but there are some frequencies outside. They're not completely zero, but they're decaying, right? Now with CNO, you approximate these frequencies. It's not exact. You approximate these frequencies. You can see that here, in particular, there are sort of expected to be low frequencies, and you have low frequencies. Surprisingly, along these lines, there are some higher than expected frequencies, still within the band limits. Otherwise, it wouldn't be a ReNO. But for some reason, it tries to expand along that direction. So who knows why that happens. With FNO, on the other hand, what it does is that it has very large frequencies here. So these are very artificial frequencies. Remember that this should be 10 to the power minus 7. It is 10 to the power minus 3. And as a consequence, we believe that these errors here, and these errors, these are from this kind of a sort of expansion, wrong frequency intake. And it's the same with the UNet. The UNet has similar structure to FNO, except that it has higher frequencies in this region, right? So the darker the blue, the smaller the values. Here you can see that there are larger values. So of course, when you change resolution, these high frequencies, they seem to, and they're all over, right? So these high frequencies, they probably cause these kind of large errors. So this is sort of some correlation between what you have with the spectrogram, your theoretical understanding, and what the actual results are. So this is the situation with respect to what happens when you think of it as a neural operator, when you evaluate the output at different grids. Now, what's also very important is what is called out-of-distribution generalization. And let me explain this concept at least a little. So what is out-of-distribution generalization? So remember that at the end of the day, these samples, the training examples and the test examples, they were drawn from some measure. Mu, which was a probability measure on your band-limited functions, BW. Because we are always working with band-limited functions, so these were on your band-limited functions, right? So this is how it looked like. Your typical sample, it looked like this. So during training, we generated 1,024 of these samples. You trained, or 768, I don't remember. You trained your architecture on it, and you got some results. Okay, so this was sort of the picture. During testing, you took different samples, which you have not seen during training time, and you checked what the errors were. And this is the whatever you get, this 3.1, 3.93, and so on. These were results on the test set, right? But now what you could do is, what if I take a different measure? So all of them are drawn from the same measure. Now I take a different measure, nu, which is also a probability measure on BW, and I sample at inference I train on this measure, and I sample or I test on a new measure. So this is what is called out of distribution, right? Because now the data that you're giving is different from the data that you generated. Or how does it mean? As you can see here, so this was some initial layer, and we had some perturbations on that initial layer, and so on. Now what we do is that we have bigger perturbations, which were not seen during training time, and we also change the location of the layer, so we move it. Okay, so this has also not been seen by the data during training time. As you can see, the output changes, means this is an example. The output was here, the ground truth, and the ground truth here is a bit different. And the question is, can it sort of extrapolate? Okay, this is always the challenge with neural networks. It has never seen this training distribution, but this training distribution is not completely off, right? It is still relatively close to each other. In other words, if you take a distance, you can't have a distance, but you can't have a norm, but you can have a distance between measures. These are close to each other. I think this, I don't remember, it depends on what metric that you take, but these are within, let's say, 50% of each other, roughly speaking. So they're not completely far. So how do these methods perform? So it turns out that the results that you get are very, very interesting. So let's focus, for instance, on CNO and FNO. So now you can see that what does CNO do? It sort of provides a right resolution to these features, right? It provides a right resolution to these features. Here, on the other hand, it introduces something that was not there before, but at least it understands that there is some distinction here, there is some distinction here, and so on. What does FNO do? It does not resolve this feature nicely. It puts it at a different place. And not only that, it puts something here, which was not there in the ground truth. And also here, remember that there is a connection between these two vortices. It simply, it does not even have them here, right? So qualitatively, you can see the difference. And the same with the UNet. Means even though the UNet and CNO are very similar to each other, you just have this additional upsampling, downsampling. You see that UNet has completely missed this entire feature here. It has just put it here, okay? And also it has put these things here. So now when you look at the predictions, you can see that, of course, all of them make bigger errors. I mean, they're not going to do, this is sometimes also called zero shot, okay? You're not having any access to the test, to this new measure. You just do it in a zero shot manner, and you can see that at least in this particular case, CNO had slightly better generalization. The error was only doubled, which is roughly along expected lines, because the measure was, the distance was like 50%, so you would expect that the error would be doubled. But here, for instance, FNO, the error was increased by roughly a factor of 3, right? And UNet also, it was increased roughly by a factor of 3. DeepONet was anyway doing very poorly in the previous regime, and it kept on doing poorly in this regime. So this is sort of an important test case for any machine learning architecture, that how well does it do in terms of extrapolation. When we change the measure, how well can it do? And this is also telling you something about the nature of the data and the nature of the model. So if you fix the data, like we did in this particular case, it is something about the model. So do we gain anything? Of course we do gain, because we have a code in my lab which is very, very fast. So for instance, on a 100 squared grid, it takes 1/10 of a second to solve this problem. So it's very, very fast. But with CNO or FNO for that matter, it takes 1,000 times less. So there is some error, but you get the results in 1,000 times less time, right? So this is the whole point of machine learning. And you'll see later on that these numbers are going to be even bigger later on, okay? But is this concept of out of distribution clear? That you really change the test distribution from the training distribution. And we will see some more extreme examples of it in the coming lectures. Okay, so this was, I have many examples, and I certainly don't have the time to go through all of them. Okay, this is also an important point. Say success is a histogram, not a point, because this was essentially, now we have, I don't remember, the test set is 256 or 512 samples. The numbers that were reported were like median errors over this set. So of course, there is a bigger spread. And if you look at the histogram, both in distribution and out of distribution, you can see that in distribution, it's clear that CNO does better than FNO and UNet. But in out of distribution is where it does really better, right? Because you can see that almost all the errors are anywhere between 3 and 8% or 3 and 10%. Whereas if you take FNO, it starts around 9% and it goes all the way up to 20%, right? So it has a better spread in terms of extreme events. Even the extremes are not so bad. Whereas with FNO, I think in this particular case, but this could be due to aliasing. That's one, we saw some artifacts due to that. Or it could be due to some intrinsic nature of the model and the data. Sometimes it's very difficult to say that. Okay, let me go through some other examples so that, okay, this is not important because I have to make a choice now. So here is another example, which is a very simple one, but turns out to be difficult for machine learning. So this is the Poisson equation. So your minus Laplacian of u equal to f on some domain, so 0, 1 squared. And u on the boundaries is, I think, 0, if I remember correctly. And then the operator just takes the forcing and churns out the u. Okay? And the forcing is taken from some measures, so the f is distributed according to a random field, Gaussian random field. Or maybe it's not a Gaussian random field, it's some signs, I think. It doesn't look like a Gaussian random field. Let's see, sum of signs. So as you can see, this is my input. You can see that it's a sum of signs, so I have taken 20 or 30 signs. And then, of course, what the Poisson equation does is that it's diffusion, so these modes are diffused out. The solution is still fairly complicated, and these are the predictions. So you have UNet, CNO. UNet and CNO are the same in this particular case, means as you would expect. The strength of CNO is what happens when you go to a different grid. FNO does very, very poorly in this particular example. Means we still don't understand why, but it does. As you can see, many new features are introduced, and it doesn't do a good job at all. And you can see that when you do an out of distribution. Out of distribution is you add more signs. So I think we took 20 signs for the in distribution set, up to 20 signs, and here it's 30 signs. So you can see that the signal is much more, let's say, wavy in some sense. And again, CNO does an excellent job, and FNO completely fails, right? It does very poorly. And this is also reflected in the results here. So this is like 0.2%. It's almost no error, and this one is like 20, 30 times more. So lot more error in this particular case. And if you do the same kind of analysis as before, again, UNet, as expected, it does very, very poorly. As you change the resolution, it's not a ReNO, so the errors go up in this U-shaped manner. Same with FNO. Actually, in this particular case, it did poorly, so there are large errors on both directions. CNO, of course, does very well here, where the Nyquist barrier is satisfied. When the Nyquist barrier is not satisfied, because remember that it's just an approximation, there were some small errors, right? And you see that beautifully in the spectrogram. So here is the spectrogram for the ground truth. For CNO, it's almost an exact match. FNO has all these high frequencies where there shouldn't be, as does UNet, right? So this problem shows that aliasing is a real concern. If you have aliasing, then you end up with these kind of artifacts, right? And then I have many examples. I don't want to give all of them because there is no time. Maybe I focus on a couple. So this is a very, very simple problem, transport equation, okay? And what does transport equation do? So transport equation is essentially ut plus c dot grad u equal to 0 in 2D. So all the tests are in 2D. C dot grad u equal to 0. C is a vector now, C1, C2. And then your solution, u of x, y, t is equal to u naught of x minus C1t, y minus C2 of t. So a very, very simple problem. Of course, a machine learning algorithm doesn't know that this is a simple problem. It just has data, and it is going to see the things with respect to data. So now we take a very simple, for the in distribution, we take essentially a Gaussian bump, okay? We take a Gaussian bump, which is given here, and then we transport it, right? So we transport it with a velocity field, which will take it in this direction. So the output is like this. And for the initial distribution, what we do is that we change the strength of the bump, we change the size of the bump, and so on. The location is always around these points, okay? And you can see CNO gets almost a perfect answer. FNO also gets a perfect answer, as does UNet. Nothing changes, and if you look at the numbers, they are like 0.3%, 0.4%, 1.4%, and so on. I mean, all of them are good, right? But now, the challenge here is out of distribution. So out of distribution, what happens is, so during the training, it always sees the initial location of the bump in this corner, in the bottom left. Now what I do is that I keep the same sort of problem, but I simply translate the bump to the top right. Okay? And when I translate the bump to the top right, of course, this is just an advection, so it will just go there. All that is happening is essentially a translation, right? And remember that convolutions are translation invariant. Okay, that's the whole point. So, of course, CNO does a very, very good job. Not exact, but almost as before. UNet 2, almost as before. There is some aliasing, that's why the error is large, we believe, larger. FNO is not translation invariant. Why is that? Can anyone tell me why? Yeah, James? Yes. So this is once you go to Fourier, you'll destroy the locality, and then you no longer have translation invariance, and you see that. So it does some translation, but at the same time it thinks that there is some feature which is still left behind, right? So here the out of distribution performance is not good. It's like, so translation invariance is good to have, because in a lot of physics you have translation invariance, right? And what is left is the very, very poor performance, for instance, of these guys, of MLP and of DeepONet. Means these are like insanely bad. And this is not because we made a mistake. They just don't understand. Means there is no notion of space here whatsoever. And so translation is not even understood here because it's a spatial operation, right? So you see here that it just keeps, it remembers that there was something here, and now it is given something here, so it just interpolates between them, right? It completely fails. And DeepONet, it does not understand the shape at all, but it does some translation, but it keeps a very, very large feature here for some reason. So sometimes, the theory and practice are not completely uncorrelated from each other. You understand the theory and you expect certain things, and that is what is borne out in practice. So this was a good test for out of distribution performance of a neural architecture, and you see the results here. The last example that I'll give are what are called the compressible Euler equations. Means we have seen these equations before, so I'm not going to rewrite them. And again, this is this flow past the airfoil, right? So our familiar problem that we have dealt with many, many times. So now the difference is what is in the definition of the operator, okay? So earlier you have seen that the operator was from the initial data to the final time. It was from the forcing term to the final time and so on. And now you can see that this is a slightly different operator, because the operator, roughly speaking, is a mapping from the shape to the flow. Okay, so that is the definition. And what is the shape here? The shape is defined in terms of the shape of the airfoil, which is given as a mask. Okay, so it gives you 0 values here and some non-zero, or 1 values here and 0 values here. It's like a mask. That is the input, and you check it from in distribution and out of distribution. Out of distribution, you simply have more basis functions. Remember that we had this Higgs-Henne functions, if you recall from some of the previous lectures. So I think here we take 20 and here we take 32, or 16 and 32. The numbers could be wrong. They do a good job, the machine learning architectures. CNO, for instance, where is it? Here. This is in distribution and this is out of distribution, does a good job. In distribution, very, very accurate. Out of distribution, fairly accurate, but not completely. As you can see that the shock is right here. It has moved a bit. It has diffused it out a bit, but it's just a bit. That's why you get 0.62. FNO, for instance, does also a good job, but it has these artifacts. You see here and here. Again, this is the sign of, we believe, of aliasing. Okay. UNet, similar, but UNet does not alias as much in this particular case, right? It has perhaps more diffusion for some reason. And why did I show this? First of all, the performance is very good. The point here is, to generate any of these results with a traditional numerical method, even with a very optimized code, this will take me 100 seconds. Okay, because this is a harder problem, this will take me 100 seconds. CNO, FNO, any of these, it takes, again, as before, right? The inference time is 1/10,000th of a second. Okay, so once you have a trained neural network, you can do things even in 2D 6 orders of magnitude faster. So if you wanted to do design, airfoil design as before, and you needed 1,000 iterations, this would take me 1,000 times 100 seconds, which is a lot of time. This will take me 1 second. So this is less than 1 second. It takes time to, of course, set things up. Yeah.
Is
Yes.
The CNO starts to give really bad performance as well.
This is because, the set of shapes is, you can't go completely crazy with shapes. For instance, if I would have taken 50 of these XNF functions, I'll get shapes that are not feasible anyway. So even the flow itself does not make any sense around them. So in the regime that we have for this particular airfoil, it will work in every case. Okay. What is interesting is what happens if you change the inflow conditions, because the inflow conditions here can be very, very different, the angle of attack and so on and so forth. I think with our preliminary tests, because you can't change the angle of attack from 1 degree to 5 degrees, then your plane will certainly crash. Okay, so you don't want to simulate that, or 10 degrees. So within the bands, because engineering is along narrow bands, you see, then it sort of extrapolates quite well. But that doesn't mean that if I change the shape entirely, it will do a good job. Means I change a different parameterization altogether, that may not do such a good job. So these methods have their limits. They are not without limits. You'll see the limits very soon. Okay, so this was actually the sort of results. I somehow made a mistake because the number was not 3.1, it was 2.76 and 3.57. But roughly it is, you can see that there are different examples, and it's always a similar story. The strength of CNO is in the fact that it has this ReNO property, right? So you don't have aliasing errors and so on. And the last point, which I want to talk about, is a little bit about computational efficiency. Not in terms of inference, because inference is always very fast. What about training? So training is epochs, right? You have to run for different kinds of epochs. So in this particular case, I think, roughly speaking, we just compare with FNO. Where FNO is the most good baseline in some sense. And you see that in terms of time per epoch, model size also, but in terms of time, it consistently was better performing than FNO. In particular, if you take, here is the sort of the bottom line, it's around 4.2 seconds, and with less error, you could train in 3 seconds. So, the training time is comparable. Actually, it's a bit faster even, right? So in other words, per epoch, it takes about 3 seconds. So if you take 300 epochs, it will take 900 seconds to train. Okay, so this is roughly the constraint. Of course, these are relatively small models. I think these are like 3 million. Perhaps the FNO was 7 million in this particular case, and CNO was like 3 million. So these are not big models. They're still much bigger than what we saw before, which was like 10,000 parameters, right? Remember, I had these examples with 10,000 parameters. But the biggest models that we have are like 400 million parameters, and this takes a week to train. So of course, there is some scaling issue, but we are going to address the scaling issue next week. Okay, so with this, it seems like everything works, but you'll see that that's not the case. There are several issues that we are going to deal with on Friday. Okay, so let's meet again on Friday, and then we can take it from there.